So earlier, we did some simplification of complex fractions, and we ended up with some weird claims, right? We claimed that 2½ over 5⅓ was equal to 15/32. If you don't remember why we said that, that's okay, because this should look like a weird thing to say. What? Why do I think that? I did some division and that's what fell out. But this seems like a strange claim. Certainly I don't see any obvious way that I could go from this back to this. Earlier when we were writing equivalent fractions, we could simplify and go back. Or if we'd simplified, we could multiply and go back up and just see if we could get back where we came from. But now we're making these really weird claims, and we want to decide whether they're true. A sentence like this, and it is a sentence, right, because it has an equals sign in it. A sentence that says that two fractions or complex fractions are equal is called a proportion. And so the question that we want to answer before we do too much more with these complex fractions is, how can we know whether or not a proportion is true? Before we use this on complex fractions, let's think about what happens with ordinary fractions. Let's say I did this. I'm going to start with the fraction 5/7. And I'm going to multiply the numerator and denominator both by 2. Again, you see I'm multiplying the numerator and denominator by the same number, so that's going to give me an equivalent fraction, 10/14 in this example. I could also have multiplied the numerator and denominator both by 3. And that would give me another equivalent fraction. Again, notice, multiplying by the same number. So another equivalent fraction, 15/21. But if 10/14 is equal to 5/7, and 15/21 is equal to 5/7, then it must be the case that 10/14 is equal to 15/21. Oh, that's surprising though, right? There's no whole number I can multiply 10 by to get 15. There's no whole number I can multiply 14 by to get 21. So there's no obvious way I could go straight from 10/14 to 15/21. I could write each of these fractions in lowest terms, see that in lowest terms they're equal, so they must have been equal before. But writing fractions in lowest terms is kind of hard, right? And isn't that what we wanted to check worked anyway? So I'm going to show you something that's going to look like a trick at first, and then I'm going to go back and show you why it works that way. Ready? What we're going to do is look at what happens when we multiply the first numerator by the second denominator, and look at what happens when we multiply the first denominator by the second numerator. These are called the cross products. One cross product, and it doesn't matter what order I take these in, by the way. One cross product will be 10 times 21. That's easy. That's 210. The other cross product will be 14 times 15. That's a little trickier. I'd better write that out off to the side. 14 times 15. 5 times 4 is 20. 5 times 1 is 5, 6, 7. Cross off the old carries. 1 times 4 is 4. 1 times 1 is 1. Hey, look at that. I got 210 again. And that's always going to work out that way. If a proportion is true, then the cross products will be equal. Why? Why would that work that way? Well, let's look at what's going on here. Remember where that 10 came from? That was 5 times a 2. And the 14 was 7 times a 2. What about the 15 and the 21? Well, the 15 was 5 times a 3, and the 21 was 7 times a 3. So when we took the first cross product, we had a 5 times a 2 times a 7 times a 3. When we took the second cross product, we had a 7 times a 2 times a 5 times a 3. Notice, we have the same 4 numbers here. And of course, because multiplication is commutative, I can shuffle these numbers around however I want. Of course those products are going to be equal. So, why are the cross products equal exactly when the proportion is true? Because of what we mean by equivalent fractions in the first place. The process of taking the cross products and comparing them is called cross multiplication. So this phrase, cross multiplication, or cross multiply if we want to use a verb, refers specifically to doing this multiplication and doing this multiplication and saying the results are equal to each other. When you go to cross multiply, you have to be looking at a proportion. This symbol in the middle has to be an equal sign. And you're going to say that the cross products are equal to each other and decide whether that's true. So we could cross multiply to check whether 5/8 equals 20/34. To do that, first we would take the cross products, 5 times 34 and 8 times 20, and we want to see, are they equal? Again, notice, this symbol in the middle is an equal sign. This is a sentence saying that two fractions are equal. If this were not a proportion, then what we're doing right now would be complete nonsense. So, is it true? Well, let's see. 8 times 20, 8 times 2 is 16, 8 times 20 is 160. 5 times 34 is a little harder. Let's work that out off to the side. 5 times 4 is 20. 5 times 3 is 15, 16, 17. Is it true that 170 equals 160? No. What does that tell us? It tells us that these original fractions were not equal. That is, the original proportion is not true. Now, when are we going to use this, really? Because this fraction looks pretty easy to simplify, and I think it's pretty obvious that it's not going to simplify to 5/8. The time when we're going to use this is when we have at least one complex fraction in play. So we might want to use cross multiplication to check whether 5/7 over 8/5 is equal to 25/2 over 28. So the only difference between this exercise and this exercise is that the multiplication down here is a little bit harder to pull off. Actually writing down the cross products, exactly the same. I'd like you to pause the video now and do just the cross multiplication step. Don't work out the multiplication problems that you get. Just write down the cross products and the statement that they're equal. Pause the video and try that now. Okay, so it'll be first numerator times second denominator, first denominator times second numerator. So we'll have 5/7 times 28, and we want to know, is that equal to 8/5 times 25/2? Okay. Well, to decide whether these are equal, I guess that first we'd better just multiply, hadn't we? So let's see. Over here I'll have 5/7 times 28 wholes, which will be 5 times 28 over 7 times 1. You know what? I'm looking at this. I'm seeing an obvious common factor because 7 goes into 28, doesn't it? I wouldn't necessarily have to simplify here, but I happen to see an easy way to simplify, so I'm going to go for it. 28 is 7 times 4. Cancel the 7s. I'm just left with a 1 in the denominator. I have 20 wholes, which is just 20. Hey, that was pretty easy. Let's 8/5 times 25/2. I don't see any super easy common factors. I think there's a 5 and there's a 2, but this multiplication looks really easy too, so I'm just going to do it. Right, 5 times 2 is 10. 8 times 25, let's see. I could write this out, or I could plug quarters into the vending machine. 25, 50, 75, 100, 125, 150, 175, 200. If I wrote that out, I would have 25 times 8. 8 times 5 is 40. 8 times 2 is 16, 17, 18, 19, 20. We get the same answer, of course. Oh, look at this. I can cancel a factor of 10 really easily. I get 20 again. Is it the case that 20 equals 20? Well, yeah. Since the cross products are equal, the original complex fractions were equal. That is, the proportion is true.